You have an advanced calculator, but how it worked, okay? What's the basic idea behind this? So to op amp. So that's why the op means operational. Okay? And then next one is amplifier. So it's called op amp. So op amp. So it's called op amp. So in the future, I'm not going to tell you operation amplifier. I'm going to use op amp, okay, all the time. It's easier. So how we can do that? So supposedly you pull out a wire. This is your wire number 1. You have another wire number 2, and of course your ground is here. Your ground is here. So I want you this. This is the signal 1 is time varying. The signal 2 is also time varying. I want you to do S equals S1 plus S2. So this is already called a summation operation for these two. I want to perform that operation, how I'm going to do it. So this is another wire, okay? So this wire says that. So how I get, so if you say, oh, I just put these two terminals get together, is this going to happen? I'm sorry, this is not going to happen. Okay? This is not operational. You put this one here, this is the same. So it's not going to work. So you cannot do that. There must be something inside here to make it a summation. And by the end of next week, it will be 100% clear to you how to do that. How to put these two signals, adding them together, construct it to another signal. Okay? Another signal. Okay, so I'm talking about signal. So usually when you do this, the fundamental building block, it turns out it's not like this summation. The fundamental block is called amplifier. So you have a signal in here, you have a signal 1 in here. I want to have a signal here, which is also signal 1, S sub 1, but I want this has a K in front of it. K is a constant. It's like this from this one is like a K. I'm amplifying this signal. Okay? This is needed in many cases. See, like I have a microphone, then I want to amplify so everybody can hear. Okay? So my voice is not strong enough. You cannot hear it. So we have an amplifier, I have speaker, right? This process is needed. So the fundamental building block is the amplifier. So because of we have amplifier, we based on this amplifier. So because of that, we can start to do operation. So we are going to move from here. So if you feel this is easy for you, you can do something else. I'm fine with that. However, if this is something you are not very sure how they add together, how we can put a signal bigger than this is called in and out, how to amplify it. If you have no good idea, it's time to focus, because this is really the building block for us. Okay? And of course, 100% it will be in the midterm and final exam. So 100%. And I'm going to give you extensive homework for next week on amplifiers. Okay? So then you will see at that time, having something integration of this, I want to get integral of this signal to you, that time is so easy. Okay? So easy. So we are going to move forward. So you can hear that. Let's see some applications. It's everywhere. So you have earphone, you have amplifiers, okay? So everywhere, okay? Amplifiers, and you see the power amplifiers, and all those things. It's a Wi-Fi repeater extender, right? So sometimes the Wi-Fi is so, signal so weak. So you can go to somewhere and buy the extender, the amplifier, and again you get it. So those are the applications. There are more applications, okay? So like in many of these 3-channel, CH stands for channel, RTF stands for what? Ready to fly, okay? Helicopters you buy on the toy, there are a lot of amplifiers in there, okay? A lot of amplifiers in there. So there's also servo amplifier. So if you have a simple signal, the signal cannot drive the motor because the motor needs power to turn, right? However, your control signal is so weak, you cannot do that. You have to amplify it. It turns out that this is the final amplification, okay? Amplification. Okay? So, and more applications like RF, like TV satellite, antenna amplifiers, so on and so forth. Okay, so those are amplification circuits. So you will see a transistor in here in the center. So previously, this is so complicated to do the amplification. Okay, so more applications. Some motion sensors, then temperature sensors. All those sensors need, the signal is so weak, we need to amplify them. Okay, all those sensors. So initially, the signal is very small, so you need to use the amplifier. Okay, if you go to hospital, most likely you need an amplifier to amplify your signal, right? To be able to visualize. So what we are going to talk regarding the amplifier is, first, let's study the simple amplifier concept. So remember, I have a signal in here, and I have signal in here. I want the signal to be amplified. Okay, so the input is small, output is big. But we need to answer the following question. Okay, following question. What is, how much amplified? So that's called gain. Gain is amplified. So you invest the money to the stock market, then you got a gain, so you got to amplify. Amplification of your money, so amplify. So it's called gain. I think the gain is a reasonable word, right? So, however, you learn in the circuits. Anything you look to this side, however complicated this part is, but to us, this is nothing but a signal source. However, in the signal source, we should always consider, do we have output resistance? Do we have input resistance? And stuff like that. So operational amplifiers, we start with very easy ideal op amps. So we are going to continue. So the gain, of course, is very simple. So this is inverting. So you amplified but inverted. So it's like you have negative sign. Okay? So it's called inverting. So this is simple. So then gain can be positive, can be negative. Now you agree? Can be positive. This thing is a real number, can be positive, can be negative. Okay? Output is simply amplification and diversion of the input. No shift in the phase. So it's called non-inverting. So non-inverting, so this is inverting. Non-inverting is the same shape, same period, but just amplitude is different. So no phase difference. So now come to the point we need to get familiarized with a concept of dB. Do you know the dB? Decibels. And when the dB was invented, okay, so it is a logarithmic unit related to the power of the gain. Power. So it's 10 times log 10 the power. Okay, so it's 10 times of log 10 the power. However, remember, power is V squared divided by R, right? And power is I squared times R, right? That's the power. You learn circuits, Ohm's law. Power is I times V, right? Is V squared divided by R, or I squared times R, right? Is okay? So the power equals I times V, right? This is V squared divided by R, right? Or the I squared times R. So this is so clear. So clear. But R is a constant, you don't change, right? So only those V is changing. So that's why we always have this type of a 20 log 10 type of thing. It's called the gain in the dB is 20 log 10 in terms of signal amplitude. So this is signal amplitude, the ratio of the signal amplitude versus the ratio of power amplitude. So the power ratio log 10, the base log 10 times log this ratio is equivalent to the 20. So where is this 2 from? From here. The 2 is from here. So log V squared is 2, right? So it's 2 is from here. Or here. Either way. So I and V is called signals. Okay? And this is the power. Okay? So any questions at this point? So in the future, when you see 20 log 10 of the signal ratio, you should understand is 10 log 10 power ratio. Is this clear? Okay. So that's useful. The reason is the overall gain is a multiplication of an individual gain. Okay, as you'll see that. So suppose you have so this is called a single stage amplification. Sometimes this is not enough. I want to amplify further. So you cascade another one. Okay, this is a cascade. So what's the end result of the amplification? A1 times A2. So you introduce the dB, it will convert multiplication to summation. You learn that. The reason to introduce log is to turn multiplication to the multiplication like this into the summation. So is this clear? So dB. Okay. So if it is 0 dB, means 1 to 1. You didn't amplify, right? Okay. Log 1, whatever, log 1 is 0. So 0 dB. So 0 dB is not 0. 0 dB is 1 to 1 amplification. You didn't do the amplification. 0 dB. So let's look at the ideal amplifier here. So what is ideal amplifier? So you understand that ideal amplifier in here is a box seeing how to connect to the rest of the system. So you have a gain A. So you have signal source, Vs, the source. S stands for source. R sub S is the source internal resistance. Okay, internal resistance. So the dashed line here, inside here, this is an ideal amplifier, but the signal source is a real source. It must have some sort of R sub S. The R sub S is never 0. It's never 0. Okay? And then you have load, R sub L. L stands for load. Okay, I just said it. Okay, source and load. And you have a amplification in there. So we call the input terminal connect to the source, modeled as a Thevenin circuit. So no matter how complicated this could be, but they can be equivalently written as a source and an internal resistance. So output terminal is connect to the load. Okay, so the load. So inside amplification, we can regard this one as some sort of voltage controlled voltage source, a voltage controlled voltage source. So to this side, like there is a voltage providing to drive the load with an internal resistance like this. Is also Thevenin. It's also Thevenin, right? So this, you look from these 2 points inside, is also a Thevenin equivalence. Okay, so then you have source, not circle, but what? This geometric shape is dedicated used for the controlled source. So it's controlled by what? It's a voltage source controlled by another voltage. Okay? So it's called voltage controlled voltage source, VCVS. VCVS. Usually VCVS is voltage controlled voltage source. Will be enough. Okay? So this is VCVS. Okay, VCVS. And this is the control. The V in is the control. So then the A times V in, small V in, is the control voltage here. So I think this equivalence is not very strange to you. Okay? It's not very strange to you. So we look at this one. So the amplifier acts as an equivalent load with respect to the source. That's the input ports. Okay. Okay. So output ports is the amplifier act as an equivalent source with respect to the load. So depending on how you look at this. So from source point of view, the source as a person, from source point of view, that gray box is nothing but a load, equivalent load to the source, right? So that's why this is the equivalent load. Okay, equivalent load. It's called R in. The R in is called input impedance. We'll talk to that. So the input resistance R in seen cross the input. So and then dependent source VCVS and modeled above, the voltage of the source dependent on the voltage drop across R in. So A is known as the open loop gain. Open loop gain. So do you see a loop? You don't. So that's open loop. So why we say open loop? Because soon I'm going to introduce you closed loop. Any questions so far? Easy, right? But you need to follow me, okay? So the reason we introduce open loop here because in the later part we have closed loop gain, okay? Okay, so listen carefully. So output resistance R out, this one, this guy here, is called our output resistance of our amplifier. This is seen in series with the dependent source and positive output terminals here, okay? So everything, this is standard notation. Don't argue, don't ask. So everything is like that. So then look at this. So it is interesting. Input V in is less than Vs for sure. Okay? Because this is like a voltage divider, right? You have a resistor here. So the V in must be less than Vs. Vs is the source. Okay? So then, of course, this is a voltage divider. Right? Voltage divider. V in is this. So it's a factor of A through the AV in. So then you can see that then VL across to here, VL is, this is also voltage divider. So this is a voltage divider. So it's a AV in here, and this one is RL divided by this, add to this, okay? So this is simple. So you can see that VL and V in, they are connected via this relationship. Okay, so together we know that it's this cascaded the two voltage dividers. But we do have an A in there, so don't worry. If A is big, that's good. So they're dependent on both source and load impedance. Okay, load impedance. So that's all. That's why in our last quiz, you guys all wrong almost. Is because you forgot to think about this way. So this is the right way to think about. You have input and output impedance. So and also dependent on the input output resistance of the amplifiers. Okay, so different performance using different load and source for the same amplifier may result in different result. So in ideally, we hope the R in as small as possible. Okay. Sorry, R in as big as possible. Okay. And R out is as small as this one, as small as possible. Now R in is as big as possible. Okay, as big as possible. So it's called input resistance as big as possible, and output resistance is as small as possible. So that ideally 0 and R out, ideally this is 0, ideally this guy infinity, that will increase the increase the accuracy. So here's an example. So if everybody is 50 ohm in here, and A is 50, I amplify 50 times, but according to what we have, okay, so the VL equals 25 VS, okay? VL is 25 VS. While this thing will give you 50, but actually didn't give you 50, okay? Didn't give you 50. So that's very important. So you lost half of the amplification, half of it, okay? So once you put this RL in, so we said without RL, okay, without this connected, so then this is only 25 because of this one divided by this one, right? Once you add load, you drop again, another half dropped, okay? Another half dropped. So you got 12.5. So this is not what we wanted, okay? In ideal case, we hope R out is 0. R out is 0. And R in is infinity, ideally. So here's another example. So everybody is 50, A is 40, and so we cascade them. Okay. So A is 40. So you have two stages, two stages. Okay. You have two stages cascaded together. So that's for this. This is for this. So then you can just, the output was 200 VS. So 200 looks a lot, but if you have seeing this 40, ideally is 40 times 40 is 1600. You lost 8 times. All right. So the efficiency is important. We don't want to lose, like I'm supposed to have 1600 amplification times of amplification. Then in the end, the actual achieved is 200. That's not good, okay? That's not good. So then we say we have 20 amplification here, and I want this VL is 40 times of VS. How many stages? So then we don't know yet. So we just, because of the stages, same stage we repeat, we have number of n in here, right? Repeat. So then this one we want to be like, to achieve 40, then you can solve 0.5 times 10 to the power of n is 40, so n is 1.9. So obviously you need two stages, okay? Okay, so amplifiers, gain, input resistance, output resistance. These are from macroscopic level. But what's the microscopic level? So in reality, how you can achieve it? So you do something like this. This is called a transistor, multi-stage transistor circuit. So that's a little bit too hard. So then it end up with this chip. This is the earliest 741. It's legendary. This is the chip. They pack all the transistors, resistors, and inside in here. So they create, as you can see, they have a DIP, dual inline package. So it's 8 legs. So how this is done is like this. It's like this, okay? It's like this. So this is the symbol. They go about all these legs, terminals. They have definitions of the terminals. So all this is the same as this. Different terminal can be found in here, okay? And this is inside here. So fortunately, you guys don't have to learn this thing. When I was a student, we learned from here. So this is called discrete component amplifier. You use each individual transistors and resistors and so on and so forth to construct an amplifier. But right now, you don't have to go this one. You directly live with this. Okay, this is the amplifier's chip, integrated circuit. So you don't learn discrete. So, but you should know that behind this chip, inside, there are all a bunch of transistors and resistors like that. Okay? But to make the transistor work, obviously you need to what? Give it a power supply. Right? Power supply. So that's why in this leg, you have power supply in here. Usually, you don't see it very clearly. Can you? And I don't know how to enlarge it. I think I should. Is this better? Can you see it more clearly about this terminal? There are 8 legs, okay? NC stands for not connected, so it's not used. And you have V plus, V minus. They are just 2 terminals for power supply. There must be an offset now. We'll come back to that. So there is inverting and a non-inverting output. Is minus is inverting, plus is non-inverting, and there's output. Okay, there's output, and there's offset now. Okay, so that's basically so if you buy the amplifier, it will look like that. So it's much easier to use. Okay, much easier to use. So in the next, we're going to focus on op-amps about this type of thing, integrated circuits. Okay, integrated circuits. So we want to study the ideal characteristics. And so this is called a ME142 op-amp. Okay, so LM741. You can write down LM741. So when people talk about this, you know it. Okay, you know it. So okay. But let me remind you that the chip we talked about only has one op-amp inside, but usually you can buy a chip with 4 of them, 2 of them integrated in the one chip. So it's possible. But now let's talk about operational amplifier, the symbol. So you have seen that we only draw V out. Non-inverting, this is inverting, this is non-inverting. Terminals, power supplies. So that's non-inverting input, inverting input, positive power supply, negative power supply, and output. Okay, output. So in fact, there is something called AV, the voltage amplification. V stands for voltage, A stands for amplification coefficient, and V plus V minus. This is the difference between this. So the amplification behaves much like an ideal difference amplifier. Okay, so in reality. So in this 741, so do you have a rough guess what is this amplification, how big it is? Very wild guess. 1? 1 is not called amplifying. 141 is way small. Okay, bigger. 10 to the power of?
4 or 7?
Yeah, 6. 10 to the power of 6. So they can do that big. So this one. But the question is, if this difference is 1, am I going to get 10 to the power of 6? Will get somebody shocked? No, it's not. Because they cannot be higher than the supplying voltage. Okay? So it will be clamped in there, saturated in there. Okay? So in this case, just imagine that if some difference in here is over a certain milliwatt, even microwatt, then that output will get saturated, like 15 or minus 15. It gets saturated. So it's really big. Okay? So this is our ideal operational amplifier. Okay? So if we compare what we learned, the general amplifier model, we just learned this, and also this thing, they are exactly almost the same. Okay? They are the same. They are the same. They are the same. So the AV, this OL stands for open loop, because I didn't introduce any feedback in there. Open loop, because I didn't form any loop in there yet. So that's really big. That's really big. So there are three assumptions in here. Okay, listen carefully. Okay, listen carefully. Three assumptions in here. Okay. So we compare this one and this one. They're almost the same, but there are ideal assumptions. Okay. The first, we assume that Rin is infinity. Rin is really big. Okay. And the second is output R out is almost zero. Okay, R out is almost zero. And the third is AVOL is very, very big. 10 to the power of 6 is already big, right? Very, very big. So three assumptions. R in almost infinity. R out almost zero. AV open loop almost infinity. Okay? Three assumptions. So because of R in is almost zero, almost infinity, then what we can say about I sub in in blue, what we can say about it? Almost zero. Almost zero, because this is almost open circuit. This infinity means open circuit, right? Okay. So that means for this op amp, the current flow into the amplifier is almost zero. Okay, almost zero. That's very important, okay? No matter what, inverting or non-inverting. So get out is also almost zero. So basically we don't have any current getting inside in here, the triangle shade. So V out is AV in. V out here is AV in. So practically. So what about infinite open loop? I told you, you cannot get infinite voltage in here. That's not possible. It will get saturated in there. Maximum is the same as the power supply. So that's the point. If we have little bit non-zero V in here, and this one will saturate. So the amplifier put in this way is almost useless, and you don't want it. It's useless. No practical use at all. Okay? So that's why we need to introduce feedback. So here we are going to discuss this one. So if I put it in and out, okay, and put out this inverting terminal feedback to here, okay, what's going to happen? The reason is the difference between here to here is V in minus V out. So that's V in minus V out. Times A, which is open loop amplification. The A is really, really big. Then we rearrange it. V out is V in with this one. I remember when A is really, really big, this is almost 1. Okay? Say, for example, this is 10 to the power of 10. So when you do this, just do this connection, then we know that V out is V in. So this one has a very nice name. It's called voltage follower. Voltage follower. Okay, the voltage follower. Okay. So voltage follower. And that's how to make 0.5 times 0.5 equals 0.25. You need to insert this in between these two voltage dividers with finite. So that's why I gave you the quiz, and you know what's the answer today. is the same as you said wrongly last time, right? But there's a fundamental concept in here. It's about input resistance, output resistance, you know, the cascading of this amplification. So, okay. So this is called voltage follower. Voltage follower. Is it? Do I need to write a follower to you? I don't like this word actually. You don't like it. You should not like it. You want to be a leader, right? But in this previous quiz, you really need a voltage follower to make it happen. So to be a 0.25. So let's review some of those amplification applications for op-amp. Okay, so inside the op-amp, so you have seen this. Okay, so inside this one is a very classical, successful design of op-amp. It's called 741. Okay, don't ask me why. It's maybe they had the 741 iterations. They designed this. I don't know, but maybe. And so I already told you what's this. And this inside this chip is like this. And so what are those applications? There are many. Okay, you add some other components. You can do like timer 555 and so on and so forth. And so I don't have. So there's a dedicated like this thick book regarding how to use these amplifiers to do something really, really magic. Okay, magic. And so BJT stands for bijunction transistor. So it is actually described on our textbook about BJT. This is BJT. Okay, BJT is a transistor. So then you put a control signal in here. Then you put a resistor in here, so you can produce some sort of sawtooth waveform. So then you connect to the LED lights, then you know that the light will dim and up and dim and up, blinking, and you can change the frequency, then you blink differently. So that's a lot of festive lights controlled using op-amps, oscillators like this. So there are a lot of other things like filters, notch filter. So this is a notch filter and so on and so forth. Power regulator, okay. Radio receiver, and if you're very confused. So of course, you don't have that foundation. So I hope you have motivation to learn the op-amps very seriously. Okay? So you invest your time in it. Because all the practical circuits, you need to use this op-amp as your foundation. So you have to start from the basics first. Okay? So let's talk about those basic ideas. How to do inverting amplification, non-inverting amplification, how to do the summation, how to do the differentiation. So then remember, all these things are called operations, okay? You are doing something, operate on something. So that's why we call operation amplifiers, okay? So and then we have more sophisticated applications like integration, differentiation, like low pass, high pass, band pass filtering, how we construct those. So then the last, we are going to talk about physical limitations for the practical op-amp. So when you are giving a task to pick up the op-amp chip, what are the things you need to consider? And we're going to learn a magic four-letter thing. It's called CMRR. Trust me, I'll check you again and again what is CMRR, okay? But we'll tell you later next week. Okay, let's do a source follower. Okay, we have already told you that this is called a voltage follower. Okay, it's very easy. V out is V in. V out is V in. So what is the key feature? It's because of the input resistance is so big. It's almost infinite. Okay, then the output resistance is very small. But remember that if you look into this one, you have RS. Okay, so in reality, you have a voltage source, and your RS is not that small. Okay, so I want to make this one small. It's not possible to make it small. You need to spend money to buy a better one. How to make the RS small? From whose eyes? From the load point of view. You cannot. If you directly, without this thing, then if RS equals RL, then you lose 50% of your amplification, right? So something like that. So we want to make this thing small, but you cannot make it small. What you do, you just cascade the op amp in there. So looking from this side, the output impedance, output resistance is small. So no matter how big this is, it doesn't really matter anymore. That's the beauty. That's the beauty of op amp. So looking from this side, looking into this, your output resistance is the same as the op amp's output resistance is small, almost zero. And that smallness does not depend on how big this RS. So RS is big or small, it doesn't matter anymore. So that's a very important buffer for you to condition your original RS. Condition, you use conditioner, right? So you condition. So RS, previously you made it big, and now you want it to be small. What do? Add an op amp as a follower. What's your question?
Can you explain what an op amp does in terms of what the electrons are doing?
Electrons, how they flow?
Yeah, like how's it flowing?
Okay. We are not at that macro level already. We are already at the abstract level, talking about. So here, we understand that this is the current flowing inside here is almost zero. Okay, almost zero. But we do know that this voltage at this point is the same as voltage at this point. We proved that. We proved that already. Did I prove? Yes, we proved that. In this case, this one is the same as this. And if I put a resistor in here, it doesn't really matter at all. Because the current get into here is almost zero. Okay? And we should not think at electrons level from now on. We should live with this abstraction. Okay? But there are some practical issues. If my amplification A is not infinity, like 10 to the power 15, so they'll have very, very tiny. So this is not 100% 1. So how to make sure those arrows will not cause any problem? Okay? Usually it will not. Okay? So that's why at this point I think the question regarding how electrons flowing inside, we left that level of details already. We are living at here. So if you really, really want to know what's going on here, then we can still talk about this, about amplifications and how they flow, you know. But this is like half semester's work. Okay, half semester. You learn electronics, you know all the principles inside here. And we don't have to live in that detail. Okay? So don't feel confused about how electrons flowing in the circuits. No, don't ask that question at that level. Let's live in a more abstract level. Okay, so the gain is always 1, very close to 1. So commonly used as a buffer between a load and a source where the impedance may not be well matched. So the case for your last quiz is exactly 2 amplifiers with unmatched impedance. Those finite impedance, input impedance, output impedance, exactly will affect our accuracy. Then if with this buffer, those unmatched ones will not matter anymore. You feel safe just 0.5 times 0.5. So whenever we cascade 0.5 with another 0.5 with a line, our understanding is you have something in between, conditioned the input impedance and output impedance in a way exactly like this sense. The output impedance is very small. The input impedance is very big. I use impedance instead of resistance. It's more general, okay? Maybe frequency dependent. At different frequency, the impedance is different. Okay? Okay, how to prove that? We already proved. Okay? Okay? We proved using the last quiz to learn some lesson. I hope you don't forget this one in the rest of your life. These 2 quizzes will plant this feeling about impedance matching and the importance of using op-amps. Okay? So that's source follower. We also talk about voltage follower, so source follower. Okay? Again, I don't like the word follower. So usually you use the inverting op-amp. So the V out and the V in with opposite sign. So in this case, we call this this dot. So we do this. Listen carefully. I said that the difference between here and here has to be really small, because this V out maximum is the supplying voltage like 15 watts divided by 10 to the power of 10. So this difference between here is very small. And now I pull out this non-inverting terminal and to the ground. Okay? And so what is the voltage here in this dot? This dot is called dot X. Okay? It is 15 divided by 10 to the power of 10 is around 10 to the power of minus 9. Minus 9 means minus 3 is a micro. It's a milli. Micro 6 is a macro. Minus 9 is, nano. Okay. So this point, according to what I said, assume this is a 10 to the power of 10 amplification, then this is like nanowatt. The maximum possible voltage is nanowatt. So if voltage is nanowatt. So compared to this one, so this has another very interesting name. It's called virtual earth, almost ground, almost ground. So we also call it node X. Okay, node X. So this is node X. So in this sense, we talk about KCL current. So because we don't have anything here flowing inside this, so anything flowing here also going there. So what we do is KCL is V in divided by VR, V in divided by R sub 1, plus V out divided by R2 should be 0. So this guy to, this is almost 0, okay? To here, so V in minus 0 divided by this, and V out minus 0 divided by this. So these two add together will be 0 because this one is 0, okay? Then the closed loop gain will be V out divided by V in is minus R2 and R1, okay? R2 and R1, okay? So this is a negative sign, so the phase is different, okay? Different. And the gain can be set by the resistor values. And so I didn't say that R2 has to be greater than, less than R1, right? It can be greater than R1, right? So my V out can be greater than the V1, V in. So V in is 1 watt. I want this V out is 2 watt. Is it possible? Sure. I want V1, V in is 1 watt. This is minus 0.1 watt. Sure, we'll just pick up different R1 and R2. So you said, oh, what if I don't need a negative sign? Easy. You cascade another one, right? You cascade another one. Minus minus is positive. So that's the way. It's easy to remove the negative sign. Okay, you cascade another one. Well, so this is called inverting op amp. Okay, the key concept here is you don't have a current flowing inside, and this voltage here is almost nanowatt. Okay, and so you treat this one as ground or virtual earth, VE, virtual earth. So then you simply say the current here add together should be 0 because the current here is 0. Okay? It's not a magic, it's a reality actually. The reality. So then if you put something like this, you will check and oscilloscope in and out, you compare. See the phase is different. Okay? So we are going to do non-inverting amplification. So what does that mean is this is positive, this is negative. Look differently. So we hit it negative. This is inverting terminal. This is non-inverting terminal. But we do this one here. Oh. That's funny. Okay. Listen, we flipped it, right? We flipped it. Okay? So we put a signal in here, and here is R. Okay, here is R. So you can see we'll have R in because the current flowing is 0. So I in should be 0. Is that right? Yes, of course. Because we don't have current flow into it. Because the open loop amplification of this one is 10 to the power of 10. Okay? We don't have current flow into it. So in other words, the voltage in here and the voltage in here are the same, right? Yes? Yes. And also our I in here should be 0. Okay, this is a very important concept. We don't have anything flowing inside. It's so small. Okay, ignore it. So in other words, this point and this point. So we are going to work on that. So first of all, notice that I in will be 0 because nothing is flowing into the op amp. Because the open loop amplification is so big, 10 to the power of 10. So, and the limiting is like 10 watt. So think about that. So it's almost 0. So then we know that V plus means the voltage at here. This is V plus. It's the same as V in. Okay, V in. So we want to derive what is the relationship between V in to V out, how it is related. Okay, so step by step, very carefully. Okay, so because of that, I have no current in here. So then we have V out. This is an ideal voltage divider. What is the VRS? This is VRS, right? VRS. VRS is nothing but RS divided by is this guy, right? So it's a voltage divider of this one, right? So ignore this, assuming we don't have this. Okay. So then we see that V in and VRS, they must be the same. This point and this point, they must be the same because the delta between here is nanowatt. The difference is nanowatt. You agree? Because the difference is nanowatt, so then this guy, the voltage at this point, look at my point, red dot. The voltage at this point must be the voltage at this point, must be voltage at this point. So V in equals VRS. So that is this equation, okay? So do you feel strange about this? You should not. If you feel very strange about this, that means you haven't started learning op amp. So please feel very comfortable about this equation. The argument is the delta, this guy minus this guy must be 0. 0, almost 0. Okay. That delta is 0. It's V plus minus V minus. V plus minus V should be nanowatt. I told you, right? Because the reason, the consequence is because the A amplification is 10 to the power of 10. Okay? So big. Okay, because of that, then we have what? V out divided by V in. V out divided by V in. Okay? So what to do? So we put V in here. So we put VS in here, VRS in here. So we get V in equals this. Then we do V out divided by V in, then is RS plus RF divided by RS. Then is 1 RF divided by RS. Isn't this interesting? And it's always amplifying. It's 1 plus something. Okay? Okay. So I think this is clear. This is called non-inverting amplification. So usually you can, so the people may ask, so the amplification is due to this, and what is this guy? What is the R for? Good question. I cannot tell you the answer right now. It's too complicated. We'll reserve this question to the later part of the next week, maybe next Friday. It's all related to how to tune the CMR sensitivity. But there are some guidelines how to choose this capital R. Okay. All right. So after next one, summation, we can get you to the weekend. Okay. So summation amplifier. So let's return to this. Okay, listen. So you put this thing, signal here and signal here, you want them to be added. So what you should really do is like this. So this is the point here. This is the point here. You can connect this together. If you don't have this one, it doesn't make sense. Okay? So you got to have this thing to make sense. Why? Listen carefully. Okay? So, first of all, listen. We have ground in here. So this is virtual ground. Okay, virtual ground. Then we apply KVL. Oh, sorry, KCL. Okay? KCL. So this is basically same thing as non-inverting amplification. Okay? Non-inverting. So let's say the one of the current is from here, another current from here, another current from here. Add together should be 0. So there's no current flowing inside. Okay. So what we get is 2A. So this is A1 and A2 and minus sign. Okay, minus sign. So then you can add them together. So what you really need to be doing here is still you can do that. So you can do this. This is a minus. This is a plus. You put this one to ground and put this guy. You can put this one together now. Okay, put this together now. And of course, there's some since there's something like this. So this is something R1, R2. So then you put this thing RF to here. So now this is the summation. But how you can tune this one is 1 and this is also 1. Then you can choose RF divided by R1. And you can RF equals to R1 equals to R2. You can do that. Okay? You can do that. Okay, you can do that. So you can see A1 and A2 are the same. Okay, are the same. Can be tuned as the same. Okay, but what if I have so many sources adding together? Yes, you can simply do the adding together. Okay, but you said, oh, I have a minus sign here. I don't like it. You can cascade another one to change the sign. The easiest way is what we do here. So what I do here is I have R in here. I have an R in here. Then I have something like this. Minus. So this is exactly just a -1 sign. Okay? Minus sign. You should criticize me at this point. Say, hey, Dr. Chen, you made a mistake. And because this thing is considered as a signal source, internal resistor, and this is internal resistor, you cannot change it. And you assume they are the same. That's not right. If you can ask that, I will be really happy. It is true. It's not. You should not do that way. So in reality, you should put something like this. Something like this. This is kind of what's the name of this thing? Potentiometer. Yes, potentiometer. You put this one here to change so that to accommodate they may be different, and these two add together is R1 prime. This is R2 prime. So you can change this one, but you cannot change this one. Make sense? But doesn't matter. I put prime here. Now everything is right, all right? Okay. So I'll let you go Then we are going to continue the discussion on Monday. And next week's homework will be very intense. It will be intense than homework 1. More intense than homework 1. Homework 1 is already intense. So if you guys need help, come to the office hour. Okay? Yay, finally.